All right, these videos don't get a lot of views typically, but here's an introduction to graphs, the next section we're going to be covering. And now we're taking a pattern-based approach, and it's real world applications and some problems we can solve with it. Now, a graph is a nonlinear data structure that represents connections between entities. In graph theory, entities are represented as vertices or nodes, and the connections between them are expressed through edges, like you can see here. So this is a node, the yellow is a node, the lines are edges. And we're going to go through some basic components of a graph. So a vertex is a fundamental unit of a graph, usually represented as a point that holds some information or data. An edge is a connection between two nodes. An edge may have a direction, making it a directed edge, or not, an undirected edge. Now, a weight, each edge has a weight assigned to it, which indicates a cost or value associated with the connection. A degree is the number of edges incident into a node, so coming in or going out of a node. And then you have in degree, it's the number of edges coming towards the node, that is in the directed graph. And an out degree is the number of edges going away from the node in directed graphs only. So I think I say degrees, it's a combination of the in degrees and out degrees, probably. Could be wrong though. Correct me if I'm wrong in the comments. Adjacent nodes, these are nodes that are directly connected to each other by one edge. So they're side by side, connected by a single edge. A path is a sequence of nodes where each adjacent pair is connected by an edge. And then we have a cycle. It's a path that starts and ends at the same node. So a cycle starts and ends at the same node. Okay. So there are various types of graphs, each tailored to represent different relationships and scenarios. Let's explore the key types. Okay. An undirected graph. So a graph in which the edges have no direction, representing a two-way relationship between nodes. For example, if we consider each person on Instagram as a node and their connection with other users as edges, a two-way relationship occurs when person A follows person B and person B follows person A. So they're mutuals. Okay. Next, we have a directed graph. And now it's a graph in which the edges have a direction, okay, indicating a one-way relationship between nodes. For example, if person A follows person B, but person B doesn't follow person A, it's a one-way relationship. In a directed graph. Now, a weighted graph is a graph where the edge has a numerical value associated with it, indicating the cost, distance, or some other relevant measure associated with that connection. For example, if each person's connection with the other person has some weight attached to it, then the weight of 8 represents a strong connection between person A and B, and the weight of 3 indicates a weaker connection between person A and C. Now, a cyclic graph is a graph that contains at least one cycle, which is a path that starts and ends with the same node. For example, person A is friends with person B, who is friends with person C, and finally person C is friends with person A, completing the cycle. Now, an acyclic graph is a graph that contains no cycles. That is, there is no path that starts and ends at the same node. For example, person A is friends with person B, who is friends with person C, and finally person C is friends with person D, not creating any cycle. And these are visual representation of each of what we just discussed. So undirected, pay attention to the lines connecting them and the difference between the lines in the undirected and the directed case. Okay, so this is an undirected graph. This is the same graph, but this time directed, as flows. Now it's the same graph, this time weighted. Now this is a cyclic graph, right? They're pointing out that we've been looking at a cyclic graph so far. Well, I mean, in this case, this directed cyclic graph. And now we have an acyclic graph. There's no cycle because this is directed, but none of the directions point back to the same node, form a path that points it back to the same node. And yeah, so then graph representation. So graphs are usually represented as either an adjacency list or an adjacency matrix in order to solve graph related problems. Now, a list is a collection of lists where each list corresponds to a node and contains its neighbors. In the case of weighted graphs, the weight is stored alongside the corresponding nodes. Otherwise, a default weight of 1 is assumed and is often omitted from the list. Now, for an adjacency matrix, we have a 2D array where each matrix indexed at I, J represents the edge between nodes I and J. The value of matrix index at the cell indexed at I and j for the particular matrix equals 1, or the weight in the case of a weighted graph, if there's an edge between nodes I and j and 0 otherwise. Okay, so these are the different representations. I find that we use this adjacency list method more in the coming solutions. At least I've recorded the next 2 solutions and we use this in it, not this. So this is a graph. This is what it looks like visually, right? But this is what we would look like if we're representing it in code usually. So a list with pointers to the next thing, or an adjacency matrix with zeros and ones indicating whether there's a connection between each of the nodes. Now this is how we can do it. Weighted. As you can see here, I put the weights in the spaces, and this is when it's undirected. So it's a two-way relationship. So for every A to C, there's a C to A, and it looks like this. Okay. Now this is weighted and undirected, and we have the same thing. For every A to C, there's a C to A, and so on and so forth. Okay, now to solve these related to graphs, we should have a good understanding of traversals, graph traversals. And based on these traversals, man, that's hard to say, some graph algorithms. So there are 2 fundamental graph traversal techniques: breadth first search and depth first search. Let's deep dive into these traversals. Traversals. So depth first search. So we're going to look into depth first search and breadth first search. And if you're taking an algorithms class or in college, you probably have seen this before, really. But again, all this information is online, so you can learn it online or learn it in school and get credit for it. So in depth first search, the strategy is to explore as far as possible along one path before turning back. Okay. Now it starts with a chosen source node and proceeds to one of its neighbor nodes while marking the source node as visited. From there, it goes to one of its neighbors and marks this newly traversed node as visited. This continues until it reaches a node with no neighbors. Now the algorithm starts backtracking. Ooh, we've done a whole series on backtracking a couple of chapters back. In backtracking, the algorithm goes one step back and checks for the remaining neighbor nodes that are yet to be explored. Okay, and this process continues until all the nodes in the graph that are reachable from the source node have been visited. Now we can implement this algorithm using a stack. When you see stacks, tend to also think recursion. Initialize an empty stack, choose a source node, push it onto the stack, and mark it as visited. While the stack is not empty, pop a node, explore unvisited neighbors, push them onto the stack, mark them as visited. Continue this process until reaching a node with no unvisited neighbors. Then backtrack by popping from the stack. Repeat until the stack is empty, ensuring all connected nodes are visited. Now this is an illustration showing how it works on a graph as discussed above. Right, so this is what it looks like in a diagram. So we have this stack we want to traverse. We put it into the stack, and then we pop it. So we've seen it before. We pop it, and then we push it into, we mark it as visited, and then its neighbors, its immediate neighbors, are put onto the stack. So E, C, and E are put onto the stack. Then we evaluate the thing on the top of the stack. In this case, E. We put E's neighbors into the stack and we mark E as visited at the same time. Pop it off the stack, and so on and so forth. Do the same thing with F. Put its neighbors into the stack, D and B. Pop it off the stack and take care of the thing on top of the stack, B. We've seen F before, and so there's nothing to put onto the stack that we haven't seen before. Take it out. Same with D. Take it out. And then finally C. We're done. Get rid of it. We're done. Yay. Depth first search. All right, now breadth first search. Now in BFS, the strategy is to explore the graphs in layers, one level at a time. The algorithm begins at a chosen source node and visits all its immediate neighbor nodes while marking them as visited. It then moves on to visit the neighbors of those nodes before proceeding to the next level of neighbors. This process continues until all the nodes in the graph that are reachable from the source node have been visited. we can implement this algorithm using a queue. So stacks for DFS, queues for BFS. Initialize an empty queue, choose a source node, and we did a lot of this in the topological sort pattern. We found ourselves using queues a lot because a lot of it was breadth first search. Now we initialize an empty queue, choose a source node, on-queue it, and queue it, and then enter a loop. Within this loop, the algorithm dequeues a node from the front of the queue, visits its immediate neighbors, marks them as visited. These neighbors are subsequently enqueued into the queue. The queue plays a crucial role in determining the order of the exploration, ensuring the nodes at the current level are processed before progressing to the next. This iterative process continues until the queue is empty, signifying that all reachable nodes from the source have been visited. Now, the following illustration shows how breadth first search how BFS works on a graph, as discussed above. And if you watch the topological sort playlist, you would see that we use queues quite a bit. And we didn't call it BFS then, but it was pretty much BFS. So we add the first thing to the queue, and this time we're using a queue. So the first thing that comes in is the first thing to go out. And we mark it as visited. Up next, we evaluate all its immediate non-visited neighbors. Okay, we unqueue both of them. And now we dequeue the thing in front, right? It's not a stack, so we're not evaluating E, we're evaluating C instead. And so we put its immediate neighbors, C's immediate neighbors, which are D, F, and B. Add them to the queue. Next, we're going to evaluate E. Do the same thing we just did with E. Put it into the queue if it's not been there before. All its neighbors have already there from C, so we don't need to do that. Mark it as visited, and then just move through the queue, like so. The exact same thing. All right, and that's all. We've traversed this graph in a breadth first search pattern. Now, traversals can be used to find paths, cycles, or connected components within graphs. However, when aiming for specific objectives, such as determining the shortest path rather than any path, or identifying the minimum spanning tree instead of connected components, traversals can be adapted to address particular optimization problems associated with the graph. There are various algorithms that help us solve these specific graph problems. We'll go over a few. There's Dijkstra, named after a guy. It's a variation of depth first search that finds the shortest path between two nodes in a weighted graph. Bellman-Ford, and I believe they teach you these in, like, again, algorithms, algorithms design courses in college. Bellman-Ford is a variation of breadth first search and finds the shortest paths in a weighted graph, even when negative edge weights are present. Then Floyd-Marshall, breadth first search variation, finds the shortest paths between all pairs of nodes in a weighted graph. Topological sort, there we are. Remember this guy? So it's similar to DFS and orders nodes in a DAG, so a directed acyclic graph to satisfy dependencies. I think most of our cases were actually breadth first search because we ended up using queues, not stacks, but I digress. Prim's algorithm, it finds the minimum spanning tree of a connected undirected graph. Kruskal finds the minimum spanning tree of a connected undirected graph. And while I don't go into all of these in this series, you can look them up. They're not things you usually encounter every day, like in everyday work as an engineer. But just knowing they exist helps you in case you see anything that's similar to them down the line. So I know one of the problems we're going to do, one of the commentary, they're going to talk about how we're using Dijkstra to solve this problem. And we've seen topological sort before. So this is actually useful, I guess. They're all really useful. I mean, if you use Google Maps, you're probably using one of these all the time. So yeah, something you can definitely look at the implementation of and use from a standard library or something to get things going. Now, the following example, actually probably not going to be in a standard library, but implement yourself or find an implementation online if you need it. Now, these examples illustrate some problems that can be solved with this approach, with a with graphs. Find if a path exists in a graph. Given the source and destination node in a graph, determine whether there is a valid path between them. The graph can either be directed or undirected. Return true if there's a valid path between the source and destination and false otherwise. Okay, so we have a source and destination node. A graph is either directed or undirected. Find if a path exists. This is like a pathfinding problem, which is like a Google Maps if you're going to pick Google Maps. So you perform a breadth first search by adding the source vertex to a queue, dequeue the vertex from the queue, add its adjacent vertices into the queue, repeat the above processes until the queue becomes empty. During this process, if the destination vertex is found in the queue, return true. Otherwise, if the queue becomes empty and the destination is not found, return false. Okay, fairly straightforward. They use breadth first search. For this one, in a directed search graph, they're doing the same thing. Okay. And I think you could probably even use depth first, either one, to really find a path, if a path exists between either of them. Then if you want to find if the cycle exists in a graph, whether there's a cycle or not, it can be. Okay, so how do you check if there's a cycle? You can use depth first search. Okay, push any starting vertex into the stack, mark it as visited, pop the vertex from the stack, and for each of its adjacent vertices, if the adjacent vertex is not visited, push it onto the stack and mark it as visited. If it's already visited and a cycle exists, so return true. Repeat the above process for all vertices, and if all vertices are processed without finding a cycle, return false. So if you see something you've seen before, just return true. Okay. And then same thing. In this case, I use breadth first search, depth first search. And you could have used breadth first search either way as well. So now, how do you know if it matches this pattern? If there's a relationship between elements. So there's a network of interconnected objects with some relationship between them. That is, the data can be represented as a graph. And here are some real world problems. So many use the graph pattern. And let's check them out. Routing. So the graph representation helps to visualize the computer network, where nodes represent devices such as computers or servers and edges signify connections. Then graph algorithms like Dijkstra's can be used to find the shortest and optimal path between any computer and server. This is to ensure that data travels quickly from your computer to a faraway server on the internet without getting stuck or slowed down. Flight route optimization. Airlines use graph-based algorithms to optimize flight routes. The airport network can be represented as a graph, where nodes represent airports and edges represent flights connecting them. The algorithms can be used to find the shortest route between two airports, reduce fuel consumption, and minimize flight time. Super useful. Epidemic spread modeling graph algorithms can be used to predict how a virus might spread in a community. Imagine people's nodes and their interactions as edges. Algorithms simulate how a virus could move through these connections to help plan prevention strategies. Okay, now recommendation systems. Online streaming services like Netflix suggest movies you might like based on what we've watched using graph algorithms. Imagine all the movies and viewers as nodes, okay, with edges connecting similar movies or people who like the same things. Graph algorithms can analyze these connections, finding patterns. If people who like the same movies as we did also like other movies we haven't seen, the algorithm suggests these new movies to us. So it's like having a friend who knows our taste in movies and recommends something they think we'll love based on what we've enjoyed before. So now we're going to do this strategy game. Select your problem on the left, clicking on it, and click one of the two options on the right. So we have two paths, A to B, shortest path to reach that. That's a graph problem. Three colors, 0 and 2, sort the array in place so the elements of the same color must be adjacent to some other pattern. We have an n by n integer matrix. If element 0 set its entire rows and columns to 0, we have a entire row and column to zeros. We have a video about this. It's a matrix pattern, some other pattern. Now we have a network of routers connected to each other. Find such a path between two routers whose removal will fill the communication across the network. It's probably a graph problem. And n by n binary matrix grid, length of the shortest clear path in the matrix. I'm gonna call it some other pattern. Am I right? Am I wrong? Could be wrong. I was wrong. I messed it up. No, it's the only one I failed. We can solve it with it. Okay. Yeah, that one was good. It involves finding the shortest clear path in the binary matrix. Each cell can be considered a node, and the presence of an obstacle or clear passage between the cells from the edges of the graph. Okay, fair. See you in the next video. Thank you for watching. You're probably more dedicated than others if you go through this video. See you around. Interesting stuff here. Look forward to even the other ones, the other videos coming down the line. Not even these ones. I'm looking forward to the depth first search and breadth first search patterns. Those are exciting. But I mean, some good stuff in here too. So stay tuned. Like, comment, subscribe, share. Upvote. Cheers.